Light bouncing off a flat mirror is highly predictable. A beam comes in, and it bounces off at the exact same angle. But a flat reflection won't help us focus light to start a fire, or spread it out to illuminate an entire room. To do that, we have to bend the mirror. Curving a reflective surface changes the angle at every individual point. Suddenly, incoming light beams chaotically scatter in every direction. Does bending the mirror break the standard laws of physics, or is there a hidden order buried inside that chaos? Controlling light doesn't require us to discover a new law of physics. We just need to look at the geometry of a sphere. The rule of reflection states, the angle of incidence equals the angle of reflection, measured against a perpendicular line called the normal. Crucially, the incoming ray, bouncing ray, and normal all exist in the same two-dimensional space, locked onto a single flat plane. This rule holds true even on a curved mirror. A single ray of light only interacts with one microscopic point on the curve, and at a microscopic level, every point on a curve is effectively flat. To find the normal on a curved mirror, we draw a flat tangent line touching that specific point of impact. The normal line shoots straight up from there, perfectly perpendicular to the tangent. The laws of reflection remain perfectly intact. The only real challenge is figuring out exactly where that normal line points for every individual spot on the mirror. Calculating a new tangent line for every single photon of light would be impossible. Fortunately, the geometry of a sphere offers a shortcut. If you draw a line perpendicular to the surface of a perfect sphere, that line will inevitably pass straight through the dead center of the sphere. A curved mirror is a section of an imaginary globe. The exact middle of that phantom sphere is the center of curvature. Every normal line on a spherical mirror is simply a radius. It connects the exact point where light hits to the center of the sphere. Once you know exactly where that center point is, you instantly know the angle of the normal line for every point on the glass. The chaos disappears. To calculate where light goes, we map the mirror's anatomy. We find the geometric center on the reflecting surface itself, a spot known as the pole. Drawing a straight line connecting that pole to the center of curvature gives us the principal axis. You can think of this axis as the equator of our optical system. It gives us a rigid baseline to measure incoming rays of light and outgoing reflections. Establishing the pole, center, and axis creates a rigid coordinate system. This transforms the physical curve of the glass into a predictable optical instrument. When light rays travel parallel to the principal axis and strike a concave mirror, one that caves inward, the geometry forces all the normal lines to point toward the center. This makes the reflected rays converge at a single intersection called the principal focus. But if we flip the glass around and use a convex mirror, the surface bows outward toward the incoming light. Because the curve bulges outward, the geometric radii point outward, forcing the light to disperse. These spreading rays never physically cross, but your brain traces their paths backward through the glass, making them appear to originate from a virtual focus point behind the surface. Whether we want to intensely concentrate light or broadly disperse it, we have total control. We just have to dictate the curvature of the glass and the position of its center. This geometric foundation is the first step toward the mirror equation. It allows us to calculate the exact size and location of an image long before the light even hits the glass.